I'm going to use this worksheet for a home worksheet I'm going to give you this video. The first problem is on Dalton's law of partial pressures, and it gives you a mixture of gases. So you just have to use Dalton's law on this. Pressure total equals pressure of nitrogen plus pressure of oxygen and plus pressure of CO2. Okay, they want to know what the pressure of CO2 is. You're given the total, you're given the oxygen, you're given the nitrogen. So you just have to rearrange it mathematically, algebraically, and say the pressure of CO2 is equal to the pressure total minus the pressure of nitrogen minus the pressure of oxygen, and that will be the solution. Okay, shouldn't be too much problem. That's just taking Dalton's law and algebraically rearranging it. Okay, for this problem they give you moles of three gases. They give you grams. 5.00 grams of O2, 7.50 grams of nitrogen, and 1.00 grams of hydrogen. The secret here is to convert all the grams to moles. Oxygen is 32. Don't forget their diatomic. Nitrogen is 28 grams per 1 mole. So you get moles of oxygen, you get moles of nitrogen, and then hydrogen is 2.02 because it's also diatomic to 1 mole, and you get moles of hydrogen. You would sum these all up, so if you sum them all up, you get moles total. Okay, and then if you want your mole fractions, you take the moles of oxygen divided by total. That will give you your answer for oxygen. Nitrogen will be moles of nitrogen divided by total, and hydrogen would be divided by moles total. And if you want the partial pressure, you would put it into PV equals nRT. For each gas, you could just show me one sample. So this would be, if I just put in oxygen and moles of oxygen, you would get the pressure of oxygen. If you put in moles of nitrogen, you could get that. There's a couple different ways to do this problem. You could plus plug in the moles of hydrogen to get that. To get the total pressure, you could just sum up all the partial pressures, or you could take the moles total and just do it to get the moles total. You could also use mole fraction. And mole fraction, we call it XA, is moles of oxygen over moles total. And you could also use the equation where you say moles of oxygen, pressure of oxygen, equals the partial pressure of oxygen times the pressure total. So it's a couple different ways you can do this problem. I want to get to 3 and 4. 3 and 4 are going to put into account dimensional analysis. They're going to ask you, what's the pressure of oxygen? So in my answer, I'm going to say the pressure of oxygen times V equals the moles of oxygen times RT. Okay, so the answer is pressure of oxygen. My pen's going to run out at an opportune time. Equals moles of oxygen divided by RT over volume. Now, they're asking you the pressure. They didn't specify which type. So if you want atmospheres, you can just choose your R to be 0.0821. If you want to get your answer in millimeters, you could have chosen 62.4. The temperature is 25, so it's 298 Kelvin. The volume in the container is 2 liters. Okay. Now, if I'm using R, I have to be careful that my volume's in liters. That's going to come up on the next problem. What I have to do is find my moles of oxygen. Okay. But it doesn't start you off with either of those things. It starts you off with grams of perchlorate. That's what we used in the gummy bear reaction to make the gummy bear explode. So if I take 4.35 grams of KClO3, I have one problem. This is a solid. So I can't put a solid into a gas equation and get an answer. But I can use dimensional analysis to go from my solid to my gas. And so anytime you have an equation, you go from whatever's a solid to what your gas is. So you go grams to moles, and then mole to mole. KClO3 to O2. And what we got is, for every one, there's 1.5 O2. Or you could have this reaction as 2 to 2 to 3, if you don't like using fractions. You still come up with 3/2, which is 1.5. Okay, all I need to do is get the molar mass of KClO3. 39.1 plus 35.5 plus 48. 122.6. So I'm mixing up gas laws, which is an equation, with dimensional analysis, which is something we've already learned. So 4.35 divided by 122.6 times 1.5. And what I get for the number of moles of oxygen is 0.0532. So 0.0532 is what I'm going to put in this. So the pressure of oxygen equals that times 0.0821 times 298 divided by 2, 0.65. 1. And that unit would be ATM. If I want to convert that into millimeters, I could just multiply it by 760 right there, and you get, that didn't come out right, 0.65 times 760. This might be 494. Sometimes I screw up on my answers. I can check it in my equation. 0.0533 times 62.4 times 298 divided by 2. Yeah, that should be 494, 495. Alright, good to catch mistakes. Let's try this one. Hydrogen gas is produced with sulfuric acid. This one has some other issues with it. The volume of hydrogen is equal to 159, and it's in milliliters. Well, I'm going to convert 1,000 milliliters to a liter and call that 0.159 liters of hydrogen. Okay, it's collected over water, and the temperature is 24, so I'm going to add that to 273, which gives me 297 K. Okay, the pressure total is 738. But this is interesting because it tells you it's collected over water. If it's collected over water, the water has a vapor pressure of 22.4. So the pressure total equals the pressure of hydrogen plus the pressure of water. So you actually have to use Dalton's law to find the pressure of hydrogen, which is going to equal the pressure total minus the pressure of the water. So I get 738 millimeters minus 22.4. I'll just assume the 4 is insignificant. So what I come out with is 716. Now, it's using torr here, and it's using torr there. Okay, so it is using torr. And I'll just put that in as torr. Okay, now, I'm going to use PV equals nRT. Okay, and I'm going to solve for the number of moles of hydrogen. What it's asking me for is how many grams of sodium there are. Now again, if I have this equation, sodium is a solid. So I can't directly use gas laws to find a solid. But I can find the moles of the gas, hydrogen. And I can convert moles of hydrogen to moles of solid, so in this problem, I'm going to solve for moles of hydrogen. I'm going to convert moles to grams for hydrogen. No, I'm not. Moles of hydrogen to moles of sodium. And from the equation, there's 2 sodiums for every 1 hydrogen. And a mole to gram for sodium, which is 22.99. Or I could just say 23. Okay, so using PV equals nRT, I didn't give you a lot of room to work here. N equals PV over RT. So my pressure's been corrected to 716 torr. The volume is 0.159. Now, I had to convert that to liters because my gas law constant R is in liters, so I'm going to use 62.4, and that's torr per liter per mole per K. Liter cancels out, torr cancels out, and the last thing is this is at 297 K, and K cancels out. So my answer for all that is 716 times 0.159 divided by 62.4 divided by 297. I get 0.00614. Okay, I'm going to multiply that by 2 for my mole to mole, and I'm going to multiply that by 23, and I get, hope I get the right answer, 0.282 or 0.283 grams of sodium. And there's your answer. So that's how you can use dimensional analysis in these problems. Flipping over to the other side, on my last video, I gave you a couple. This is root mean square velocity, RMS speed. They have you do hydrogen. They have you do oxygen. I think that was the example I used. Then put them in order of their velocity. Well, what you want to do is you want to find out all their molar masses. The heaviest one will be the slowest, the lightest one will be the fastest, and that's how you do that. Okay, I showed you how to do number 8. That was comparing oxygen to hydrogen, and then I'll go ahead and do number 9 to you. An unknown gas with the diatomic molecule speeds at only 3.55 times that of O2. What's the identity of your unknown gas? I'm going to go up here and use Graham's law, and this is just plugging into equation. So I have rate over rate. They refer to that rate over rate as rate of diffusion. Now I'm going to look at the number here. It's fractional. It's 0.355. So that means the heavier molecule is on the bottom. Okay. So the unknown gas, I would say, is heavier. So I'm going to put the unknown gas, I could call it gas X, I'll make it a squared because it's diatomic, over oxygen. Okay, that rate equals 0.355. That's your ratio. So that ratio up here equals 0.355. So now I'm going to put the molar mass of oxygen on the top and the molar mass of gas X on the bottom. Square root. I'm going to solve this. I know oxygen is 32. So this equals 0.355 equals the square root of 32.0 grams per mole over the molar mass of X squared. So this is just algebra now. I'm going to square both sides. So I get 0.355 squared. That's equal to 0.126. That's equal to 32 grams per mole over X, the molar mass of X. Multiply both sides by the molar mass of X and divide both sides by 0.126. And you get 32 divided by 0.126. The 0.126 is just a ratio, so your units are going to end up in grams per mole. And your answer comes out to be 254. Now, if you divide that in half, 254 divided by 2 equals 127. Because it's diatomic, I divided that in half because this was x squared. So 127 equals iodine, and 254 equals I2. So what's the identity of my unknown gas? And that's iodine. All right. Same thing. Your unknown gas relates at that rate. The oxygen fuses at this rate. The oxygen's heavier, so find the molar mass of the unknown gas. I'm sorry, the oxygen's faster, the unknown gas is slower. So as long as I set this up correct, I got the rate of oxygen equaling 0.0358, and that's liters per second. The rate of my unknown gas, and that is 0.0139. That's liters per second. Your units canceled out. That comes out equaling a ratio. And your answer for this one would be the molar mass of X over the molar mass of oxygen is equal to this ratio. So I'll find the ratio. 0.0358 divided by 0.0139. The ratio is 2.58. That's equal to the square root of the molar mass of X over 32 oxygen, diatomic gas. Square both sides. To solve, you got to take away the square root. So I need that squared, and I end up with 6.64 equals the molar mass of X over 32, which is oxygen. Multiply both sides by 32. And the molar mass of X is equal to 212 grams per mole. I didn't particularly ask you to find out what the gas in this one was, but you know it's 212 grams per moles. All right. That's it on effusion, diffusion, and Graham's law, and RMS speed. And that finishes out the chapter. I'm not going to do real gases for versus ideal gases, know those characteristics, but I'm not going to do the van der Waals equation. They have a van der Waals equation in section 10.9. But this finishes it out, and I'm going to give you an assessment on this in 2 phases. I have one worksheet which will be similar to the first 2 worksheets I gave you on regular gas laws, and then you're going to get another test like this that'll just be on Graham's law and RMS velocities. All right, very good. That's it on gas laws.